So very good afternoon. Lecture 20 today we'll see conclusion of our discussion on continuous optimization and some glimpses of results in discrete optimization. Of course, it's just to get you familiarized. We will not have time to do much in discrete optimization. So we had partly done this projected gradient descent for constraint optimization, but all that was part of the generalized gradient descent. That's what we are trying to conclude today. And what is generalized gradient descent about? Well, it basically starts with the idea of gradient descent and trying to take a gradient step approximation and then find the gradient step approximation is with respect to the differentiable component, right? And that differentiable component gives you an estimate Z. You find an X that is as close as possible to Z, while also ensuring that the non-differentiable component C is minimized, right? That's a basic idea. And what we saw was the proximal gradient descent, the generic framework of proximal gradient descent. But what we'll do now is the projected gradient descent in some more details. I, of course, gave you some exposure to what projected gradient descent is, right? So what proximal basically says is you have a non-differentiable component, but that non-differentiable component is, after all, not an indicator function. But the case of projected gradient descent is when the non-differentiable component is basically the constraint. C is the constraint. Okay. So in the case of projected gradient descent, you're basically trying to solve min over x f of x plus the indicator function with respect to the constraint C. So the idea here is, like always, or like you do in generalized gradient descent, you find the unconstrained descent step and then you subsequently apply the IC. But what does application of IC mean here? You want to be close enough to Z, right? So this is the prox step. So you would want to be as close as possible to Z, where Z is the unconstrained update. Okay, X subscript T. So this is the unconstrained update Z, and you want to be as close as possible to Z. Right? Let me use T plus 1 here. Just to be consistent, T plus 1. So this Z is nothing but YT plus 1 in the board. So the YT plus 1 is unconstrained update. And then you try and apply the constraint, which is nothing but projection. And what is projection? Finding the point closest in the set C, which is closest to the unconstrained update YT plus 1. Okay, that gives you XT plus 1. Because prox is nothing but XT plus 1. In the case of constrained, in the case of projected gradient descent. What we also saw is that this gives rise to a very interesting new discussion, right? We are saying only projection with respect to IC. For projection in this case basically means minimizing the squared norm distance, right? But what if you replace a squared norm distance by any other function, right? So that gets us into the space of KKT conditions. Can we actually identify closed form solutions, at least under certain constraints? Lagrange dual. These are topics we'll cover today. So these all pertain to the theoretical results of projected gradient descent. This is a little bit of a recap, right? The algorithm basically starts with an unconstrained step update and then immediately projects it back, right? All the theoretical results of convergence will hold, which we'll not get into again. Now, how do you really solve this? And we again got the intuition with this very simple example where you have a single constraint from a single function. So let's say the function is that gz is less than c, less than equal to c. So just like we draw the level curves so far, we have drawn level curves of our objective function. Imagine your objective function is f. F is 1/2 z minus x square. Okay, this is a new f. Okay, so replace this f with f tilde if you want. This is f tilde, so that you don't get confused with the f on the slide. So I'm putting a tilde on the f on the board. So this f is basically 1/2 z minus x norm squared, and I draw its level curves. The idea is that if the point of optimality lies inside g1x less than equal to c, which means g1x is actually less than c, or gx, there's only one g, gx is actually less than c at the point of optimality. If it's inside here, we would expect the normal necessary conditions to hold, which is the gradient of f should be equal to 0. Right? So we identified our intuitive necessary conditions. So which is if g1x is less, x star if you want, right? X star is less than c, less than equal to less than c, then the gradient of f at x star should be 0. On the other hand, if the point of optimality were to lie on the level curve, right, is else if g1 x star is equal to c, that is, it's a constraint which is active, then what we would expect is that if I were to move inside the constraint region, what does inside the constraint region mean? It means decreasing the value of g1. If I were to decrease the value of g1, which means if I were to move in the direction of the negative of gradient of g1, right? Decreasing g1 is negative gradient g1 descent or movement. Then my f should increase because I am trying to minimize f. If the moment I move here, f should increase, which means there is a direction, there is a gradient, there's a non-zero gradient of f in the direction of the negative of gradient of g1, right? The only condition under which I can violate, right, or I cannot be on the boundary, I'm violating the fact that there's an active, the constraint is active, is if I can reduce the function, the constraint value g1 while reducing my function fs as well. So the other way of saying is, the only way you can actually be satisfied an active, you can have an active constraint is the moment you go in the direction of decreasing values of g1, you'll end up increasing the gradient, increasing f, which is there's a positive gradient f, right? So if given x star is equal to c, then you must have that by decreasing the function value g1 at x star that is moving along the direction of negative of gradient of g1, you should have increased the value of the function f. Is this clear? This is very critical, this intuitive understanding. Okay, so this is the picture we drew. Yeah. This did not assume any properties of G1. This is a necessary condition. Okay. We have not mentioned anything about G here. This is necessary condition. For any differentiable f and c. Okay. So how do you sum up these two? You can say that gradient of f at x star 3. What I've done here on the board is I put the lambda with, I hope that's okay. I'll just switch the place of lambda. Instead of putting lambda with f, I can put the lambda with g. Right? Just be consistent with the board. Both are correct. So okay, so what basically we are saying is gradient of f at x star plus lambda times gradient of g at x star must be 0 and lambda times f of x star must be, sorry, lambda times g1 or g1 of x star must be 0. Now, is this a fair summary of what we have written on the slide? Okay, what we are saying is if g1 x star, okay, sorry, I should use, sorry. Let's take this. Okay, so now how do you compute the projection operation in general? As I said, optimality conditions are either gz is equal to c and z minus x plus lambda gz equal to 0. Now this is for the special case that f is z minus x norm square. So I'm just going back to projected gradient descent, right? So special case is what I have written on the slide. Um, projected gradient descent has f defined to be z minus x norm square. That's it. The rest is just by substitution. So what happens if you have gz to be A transpose x? Okay, so you just write down. What does it mean? If gz is A transpose x, which means the constraint was A transpose x is less than or equal to C, then either A transpose equal to C, and that is basically lambda is greater than 0, and A transpose x is equal to C. So that z minus x plus lambda is equal to 0, right? The gradient of f plus lambda times the gradient of g, which is A. Function g is gradient is A is equal to 0. If x is optimal point on boundary, else else if A transpose x is less than C, then z must be equal to x must be equal to z, sorry, right? Because this gradient should go to 0, so z must be equal to x. Basically going back to the old thing, right? If your update point is lying completely within the constraint region, right here, if the update point lies here, then there's nothing to be done. You right? There's no projection to be done. So it also, I mean, these steps are also correlating with intuition. That's all we are trying to say. Is this clear? So I hope you tried out. I mean, I spelled it out as homework. Please try out these very simple cases. What it will mean in each to project, just based on these necessary conditions. Okay. I mean, other example I took, linear system, A transpose X, which is, think of multiple such linear inequalities, right? So A transpose X is equal to B, could be less than B, whatever, right? So how do you, so here's the understanding, right? If your unconstrained is, so let's say it's less than equal to B, right? So this shaded region, less than equal to case. So then if xu is above, then you project it. If xu is within this region, right, less than equal to, then stay there. So I had kind of concluded at this point. I'd said, well, what are other possibilities? So let me okay, you can see this, right? So let's look at some of these. Z plus is when Rn plus. If you're looking at Rn plus, you're just taking the clipping it at 0, right? Let me in fact go to the next slide. That may be, I mean, the annotation here, right? What does Rn plus mean? So if you are in the positive quadrant, then just stay there. If you go into one of the other quadrants, project it back to one of the cardinal axes. Let's look at box. Box constraint is very simple again. What box is saying is the point should be between L and U. Right? What is the intuition? If you are lower than L, clip it to L. If you are higher than U, clip it to U. Else leave it where it was. Likewise, ball CR. What would you do again? Radially project back towards C. Right here. So you'll radially project towards the center. This we already, this we can easily understand. Well, A transpose X is less than or equal to B, we have done this. So this is basically projecting it. Also, this was a simplex, but this we have done. A transpose X is less than or equal to B. Right? This one, simplex. Okay, so simplex, while the constraint looks a little bit more intimidating, what you need again is to project on one of the sides. Simplex is in a lower dimension, triangle in lower dimension. I mean, triangle in the case of 3D. So you need to just project to one of them. So projection is always very intuitive here. So sometimes you can look at half spaces, intersections. So HAB, intersection box. So what if constraints are intersections? Again, it's kind of projection composed with projection. So I'm not going to go over all of these. You can. I think you can understand it yourself, right? Okay, so now we want to get a little further from here. To conclude, right, before we move further, what happens for projected gradient descent? Well, all the standard results of gradient descent carry over to the projected case, right? As long as you can do the projection quickly enough. So the cost involved in computing the projection is a black box here. Okay, so now we'll get into some more details, okay, some more understanding. What we'll do is we'll not be only focused on projected gradient descent. We'll assume that that's really a special case. What we want to really do is understand the process of solving a constraint optimization problem even more closely, right? What we did here for example, right? The question asked was there any convexity assumption? Well, convexity assumption, where did it come? It came in the convergence analysis. But the projection itself did not require, right? We just invoked the necessary condition. Here we say that all the results carry forward. Convexity, strong convexity, smoothness, all of that came only in the convergence analysis. But in finding the solution, we just invoked the necessary condition, which was stated on the left-hand side. Sorry? This necessary condition did not require convexity. Yeah. Because you see, even the vanishing of the gradient is only a necessary condition for any F. Sufficiency, for example, when we looked at subgradient vanishing, there we required convexity, but necessity we didn't require. Is it clear? So far, only the place where convexity comes up is convergence results. And that's why what happens often is you show an algorithm or inspire an algorithm, maybe often using convexity, show its convergence results, but apply it with non-convex functions. But now what we are going to do is trying to understand, for convexity, can there be a sufficient condition? Without convexity, can there be a necessary condition? Let's understand this in some more details, not just with one constraint, right, but with multiple constraints. So what if I have these constraints? I have half space and a box constraint, right? What if I have a simplex constraint and a half space and a box constraint? So remember, we talked about a lot about calculus. Now, what about the calculus of the calculus of projection? with multiple constraints. Okay, so it can we do something with? Okay, so that's what we are trying to understand: calculus of projection with multiple constraints. Um, uh, okay. Okay, so here we go. As I said, we will not just have one constraint; we'll have multiple constraints. So such that gix is less than equal to 0 for I equals 1 to m, hjx is equal to 0 for j equals 1 to n. Oh, j equals 1 to p. Um, right? So this should equip us for not only more complex projections, but also a more interesting question. There's another perspective why we are interested, not just from the calculus perspective. See, what we said is if I had to solve this problem, you can still say, oh, I'll do the following. I'll do projected gradient descent. I'll do an unconstrained update on f and then project on these. My question is, well, if there's a way I can solve for f itself, right? Why do I keep doing projection? What I did for one single projection operation, can't I do for f, right? So that's the second option. Instead of solving the constraint optimization problem iteratively by gradient descent, blah, 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 there are very interesting cases, like the support vector machine, right? You started with a primal optimization problem and you came up with these interesting characterization. And lo and behold, you came up with a very interesting new optimization problem, which gave you a lot more handle into nonlinear separability using kernels, right? So we want to do something more strategic and not just, tactically solve using projected gradient descent. So that's the option 2. Is this clear? So that these are the two motivations why we want to now really address this interesting general problem. That will give us Karush Kuhn conditions for optimality, conditions for necessary and sufficiency. So convexity will also come in. So far, convexity was kind of brushed aside. Okay, so I'm going to do a little bit of jump, focus more on the intuitions here. What did we have on the left hand side here? Right? In the name of projected gradient descent, of course, but I'm going to erase the projected gradient descent part. For a minute, generalize what we have on the left hand side. What did we say? We had one G1, G1x less than equal to C. Here we have, okay, let's replace a C with a 0, right? What's the point in keeping a C there? So we'll keep it 0. I mean, you can always absorb the C inside G1. Okay, so this is a waste of time. So I'm going to, first of all, I'm going to make a bunch of changes. So lambda G1 x star equal to 0. Now, if I had multiple GIs, so instead of just calling it G1, let's say I called it a GI. What would change? Okay, forget about H. For now, just forget H. Okay, just the G's. What would change? So I was looking at one G1, right? And what was my argument for single G1? if I am able to if I am able to reduce G1, right? Then that should result in increase in F if I'm on the boundary. The optimal point is on the boundary, right? That's how I came up with this equation. How would it change when I have multiple G1s? Just the same intuition, multiple GIs, right? What do I want? I want that the the direction of descent for F should be in the orthogonal complement of the gradients of all the GIs, right? Which means I should not be able, for a boundary point, I should not be able to move within any of the constraints, within any of the G1 or G2 or G3, right? While still decreasing F. So which means the moment I want to decrease F, I have to go orthogonal to all there. So to look at the vector space spanning the gradients of all the GIs. So instead of saying this, right, what I said earlier was gradient of F and gradient G1 should lie in opposite directions. Now, instead of saying opposite directions, I am saying that gradient of F should not have any component in the space spanned by all the gradient of G1s. GIs should not have any positive component. Sorry, what I meant is should not have any positive component. So the generalization, okay, let's. So here's a plus, sorry, this remains 0. Here's a plus. Instead of 1 lambda, I'll have multiple lambdas. Okay, just interpret this once more. Gradient of F x star plus summation over I lambda I gradient of Gi x star equal to 0, which means, and lambda is will be greater than or equal to 0. Okay, so I forgot to mention that. Okay, so lambda I should be greater than or equal to 0. Even earlier, it has to be greater than 0, obviously. Right. So what we are saying is, look at the positive space spanned by the gradient of GIs. The gradient of F should not have any component in their direction, in that space, the positive linear combination. It can be, again, it should be, it can have a component against that, complement to that, but nothing in that positive direction. Is this clear? That's it. The simple so-called generalization. And everything else will remain same. For every I, lambda I times Gi x star is equal to 0. Okay, so for all I, lambda I Gi x star should be equal to 0. What does it mean? Well, either the Gi is inactive and lambda is 0, Gi is less than 0 and lambda is 0, or lambda I is greater than 0, which will force Gi to 0. Same logic, right? I mean, because what I don't want is the inactive GIs. If there are inactive GIs, Gi is less than 0, then I don't want the lambda I to contribute. I don't want that component to be here. That's it. How does it matter if I'm sitting inside the solution space, inside the constraint region? I mean, my F, poor guy, the gradient of F should not be bothered by those gradients. Same idea. So you see a simple generalization of what we showed earlier. Is this clear? Looks like a little leap, right, of faith, but it's quite intuitive. Of course, we can do in a very rigorous manner. We won't have time. So I'm only going to focus on intuition. If you're interested in very rigorous proofs, you can go through some of my previous lectures is to do convex optimization. I'll be pasting, showing links to those videos. But this intuition should be good enough. Any questions? So here, you see. Now what we are doing is moving one step ahead. Not only we saying that, okay, sorry, this will come later. Let me show the constraint directly. Yeah, let me show this. This is what I'm talking about. The gradient of F should not have any positive component in the space spanned by the gradients of G's. I'm going to do the same thing with the gradients of H. Why? Here's a trick. Can you express Hj equal to 0, Hjx equal to 0 as two inequality constraints? What are those? Less than equal to 0, greater than equal to 0. So inequality constraint can be viewed as, sorry, a single equality constraint can be viewed as two inequality constraints. So whatever I was saying for G will also hold for H. But the only difference is because I can view an equality constraint as two inequality constraints, while for the inequality constraint, lambda I should be greater than or equal to 0. For the equality constraint, will there be any such condition on its multiplier? No, right? So this is the other leap of faith. So I'm going to just add summation over J, mu J, Hgx equal to 0, star equal to 0. But with no constraints on mu. Okay. Of course, some other constraints will remain. So this is basically our Karush Kuhn conditions. For all I, Gi x star should be less than or equal to 0. Obviously, the constraint should be satisfied. And for all J, Hj x star should be equal to 0. This is exactly the set of Karush Kuhn optimality conditions. Please ask questions if you have. Yes, good point. So lambdas must be optimal in the sense these are lambdas corresponding a solution to the dual problem. So we'll come to the dual problem, right? But you have to find the lambdas. Right? So if you want to put a star in lambda or a hat, like I've done in the slide, I put a hat around every x and lambda. So you can put a star or a hat, right? So then you must find those lambdas. But if you can find a bunch of lambdas and mu's such and x star or x hat such that these conditions hold, then that x star must then that's a necessary condition for optimality. Not yet sufficient. Did we bring in convexity anywhere? No convexity so far. Right? And so far we only looked at necessity. Now I'll come a little bit, now we'll move a little further. Okay. Any questions about these conditions? The intuition behind these conditions? Yeah. We'll show. So I'll give you an example of support vector machine, probably the most attractive example. The KKT conditions give you a way of simplifying things. We'll come to that. But did you understand the motivation for necessary? For convex, it can, yes, under certain conditions, it becomes sufficient as well. But is this necessary clear intuition? Before I move forward, yeah. No constraint on mu. No constraint on mu. Okay. And I tried to give the intuition, right? The mu's are kind of originating from considering two inequality constraints on H. Hjx less than equal to 0 and Hjx greater than equal to 0. Any other questions? Okay. So now we get into the next interesting discussion. So what we are going to do is go to the dual theory. I'm going to now define a Lagrange function. What is a Lagrange function? Well, kind of, working backwards. I saw all these necessary conditions. I saw a very interesting linear combination of the objective function and inequality constraint and the equality constraint. I'm just going to put them into a grand function called L. Why? Because I can set the gradient of that L to 0. That Lagrange function, it gives you a necessary condition for optimality, right? So that's the next step. Lx comma lambda comma mu which is fx plus summation over all the inequality constraints times lambda I plus summation over all the equality constraints constraint functions of mu j times hjx. This is my L, which is a function of x, lambda, and mu. Okay. And you'll see that I'll start doing a lot of color coding here. And the constraints gi and hg are in red. So red is basically a feasible region for x, right? But now, because I've added lambda and mu, I'll start talking about a feasible region for lambdas as well. Well, the intuition or the motivation is all lying in this necessary condition. We have gone a little ahead and then doing a little flashback, right? So the constraint on the lambdas are in blue. So you'll use this red and blue colors. Okay. Roughly the blue will correspond to the primal, so to the dual space, and the red will be the primal space. So this is right, primal feasible, dual feasible. These kind of terms will come out. Okay, so I can't do all of that on the board so nicely, so I'm just going to leave it in not too colorful, but yeah, try and put lambda j, lambda I greater than equal to 0. And this is primal feasible x, and this is we'll come to more of dual feasibility. We are not completed dual feasibility. One step into dual feasibility is lambda I greater than equal to 0. And the motivation I already gave that. Now no constraint on mu. Now the other interesting thing is, if you consider the primal feasible x, then gix should be greater than equal to 0. So it's less than equal to 0. hgx should be equal to 0. And if you consider the dual feasible lambda I, which is lambda is greater than equal to 0, then what happens to this term, lambda I gi summation? It will always be, if you consider these two, negative. Lambda I gi will be always negative. Mu j hj will always be 0. So if that is the case, you can always say that for primal and dual feasible x and lambda, Lx lambda mu will be less than equal to fx, because if you're just adding negative or 0 terms. So under those conditions, fx is greater than equal to Lx lambda mu. Right? Now, what do you get tempted to do when you see an inequality? It has x on the left hand side. It has an x lambda and mu on the right hand side. What is your temptation? You have used this trick very often, right? Sorry? Huh? You'll say, well, what about the following? Why not minimize the right hand side with respect to, maximize. You're trying to lower one, you maximize the right hand side with respect to x. Okay, x. Lambda and mu. How about maximizing the right hand side with respect to lambda and mu? As long as lambda and mu are so-called dual feasible. Lambda greater than equal to 0, blah, blah, blah. If this inequality keeps holding, then even if you do a max, inequality will hold. So this function L maximized with respect to lambda and mu, well, is one thing. But what about x itself? What if I do the following? You can also do something with x. What can I do with x? So I can maximize with respect to lambda and mu, as you rightly pointed out. Can I also do something with respect to x? Okay. So I'm just putting together all this. This is fusible region. Yeah, I've just given the same point. The rationale behind the Lagrange function at the boundary, the gradient of f must lie in the space pi under the gradient of g, h's and g's with some sign constraints. Yeah, negative. Okay, so let me get to this. So I already kind of gave you a hint that you may want to consider maximizing with respect to L and lambda. But before that, I can also consider a minimization with respect to x. Because if this holds, right? Let me erase some of this. So my optimization problem, mean of fx, such that gix is less than equal to 0, hgx is equal to 0. Now I'm considering a Lagrange function fx, which is upper bounded by fx. Now this Lx lambda mu, what if I minimize it with respect to x? I can maximize with respect to lambda and mu, but before I get there, how about eliminating x? But what x? Primal feasible x. Okay, minimize with respect to primal feasible x's, gix is less than equal to 0, hgx is equal to 0. So what if I minimize L? Okay, so this is going to be given a new name, L star. L star lambda mu is L minimized with respect to the primal feasible constraints. So far, his question is, will the point that minimizes the, see this for a given lambda and mu, the point x that minimizes Lx lambda mu while satisfying the primal feasibility, will it be the solution to my original f? Not necessarily. So far what you have written, fx is greater than equal to Lx comma lambda comma mu, greater than equal to. That inequality holds even if I minimize with respect to the primal feasible conditions for a given lambda mu. Right? It's a function of lambda mu. That's what I call L star. The x that gave me L star need not be the x that minimizes fx. No. Nothing. No assumption. Right? So this inequality otherwise holds. Is very simple, right? Now what we are saying is, well, this L, which has this particular form, is a pointwise minimum. L star is a pointwise minimum of linear functions. Why? Look at this. This is a function of lambdas and mu's. It's a pointwise minimum. And what do you know about pointwise minimum? Huh? Pointwise maximum of linear functions. So linear functions are convex and concave, both, right? Pointwise maximum of linear functions is convex. Pointwise minimum of linear functions is concave, right? So this is always a concave function. This L star, this is always concave. Did we make any assumption on the primal function f? Did we make convexity assumption anywhere? No, right? Without any assumptions, L star is always concave. That's an interesting observation. We have got concavity with a price, a small price we had to pay. The price is that there is an inequality. So we have landed in a so-called concave problem, which I can maximize, right? That was the motivation. I have a lower bound, which I will maximize with respect to lambda and mu. But before I maximize with respect to lambda and mu, I'm minimizing with respect to feasible x. So I have got a concave maximization problem, which is a lower bound to an original problem, which has no convexity assumptions. Max over lambda greater than or equal to 0 of L star lambda comma mu. Now the question is, L star itself is a little complex function. L star itself is a min over feasible x. How do you find the feasible x? Don't worry about it now. We'll come to that, right? So what we have found is for primals, if fx is greater than or equal to L star lambda mu for all primal feasible x and dual feasible lambda I mu j, we are maximizing the lower bound L star for dual feasible L lambda mu. Right? It's a lower bound for f. Okay, so while we had this original problem, what am I doing here? This I'm saying is greater than or equal to, sorry, not this. This min over f x is greater than or equal to max over lambda greater than or equal to 0 of L star lambda mu. This is the primal problem. This is a primal problem. I should have used I can't reuse blue color here. It is not very clearly visible. The L star is the dual problem. Okay.
So we get a concave
function to be maximized. Arbitrary f, arbitrary g, arbitrary h. Oh, I have not said that the maximum of L star gives you minimum. I said it is the lower bound. The max of the dual, Lagrange dual function, which is the dual optimum, gives me a lower bound for the min, original min. It is not equal to. So we come to the next question. When will it be equal to? Can it be equal to is a question, right? So this result of inequality is called weak duality. Right? No assumptions made, right? This weak duality will have the dual problem. The solution to the dual problem will be less than or equal to the solution of the primal, right? So weak duality primal solution greater than or equal to solution to Lagrange dual. This is the weak duality. Question is, when can this become strong? When can there be an equality? Okay, so I'm going to take you through another small graphical exercise, right, to help you understand this. So just register, right, the LHS has no lambda or mu. Of course, you want to minimize fx subject to g and h. G I less than or equal to 0, h j equal to 0. So I didn't write that everywhere, but I mean, it's written here, right? And the mu RHS, which has no x. So primal problem has no lambda mu, dual problem has no x. And there's a lot buried between the two. And what is buried between the two is all this, um, this Lagrange function, L star, Lagrange dual, sorry. Right? Min of x feasible fx is greater than equal to max of lambda mu feasible for L star lambda mu. Now, what we'll do is we'll represent both L star and f in a single graph and show intuitively what this weak duality means graphically, and when you think strong duality will happen, right? Some of you may already have your guesses when strong duality will be there, but don't just remove the convexity bias. Just look at, absorb the graph I'm going to show you, right? You see this graph. So this graph has been shown for a single G1. Like always, we'll try and stick to a single inequality. Multiple inequalities and multiple equalities are easier to generalize to. Okay, so what we are trying to show is two things. Remember, the dual was to maximize something. The primal was to minimize something. So our primal, okay, is going to be basically to minimize the intercept, the z-intercept of this curve. Right? This curve, what you see I, corresponds to all the points which lie above f. So let's say I have fx comma g1x, fx comma g1, fx prime comma g1x prime, right? So you keep, imagine, take all the x's in the world and plot their fg, fg, fg. So this space is basically the fg's. And what you see, the curve here is the frontier, the boundary of the fg's. Okay, I'm not, so in my detailed course, I go through a lot of definition. Here, the intuition is important. So what is happening here is this is the frontier of the FGs. And what is my goal? My goal is I want to minimize F. F is on the Z axis. So think of it as GF, sorry. G is on the X axis. F is along the Y axis. I want to minimize F such that G is, how should G be? Less than or equal to 0. So what does it mean? I want to find the lowest intercept of this curve on the on the Z axis. I can't afford to go to positive values of G, right? So basically this curve, I want to find where it intersects. As it comes from the top, intersects the Y axis. That is my primal problem. Okay, without getting lost in the definitions. Take it from me that the yellow region is the space of all x, fx comma gx, right? And what we are showing here is the frontier, the boundary. And I want to push the f as low as possible while keeping the g negative. So you understand this region. I want to kind of find the lowest intercept in the above region. That is the story of primal. What is the story of dual? The dual is basically this hyperplane, right? I mean, look at the dual problem. What is L star? L star is nothing but, it is the pointwise minimum, right? So what your report, and since it's only one, in this case, there's only one lambda. Yes, G1, lambda 1, G1, only one. So think of this as a hyperplane. And what am I trying to do? What is the dual trying to do? It is trying to push, right? Find the max of all those. So think of these hyperplanes, lambda 1, alpha 1, lambda 2, alpha 2, as basically the lambda. So instead of, yeah, actually alpha is not this. There's only lambda, there's no alpha. There's no mu. This mu is not there because we're only looking at inequality constraint. This alpha is the value of the dual. Just like the the y-axis for the primal problem was the value of the function. Similarly, the y-axis for the dual problem is also value of the function, right? And as I keep changing the hyperplane, I'm changing the value of lambda, and I'm changing the value of the y-intercept. The y-intercept is basically the solution of the dual. What do you know about this inequality. What is this inequality called? The weak duality result. So we are only interested in the hyperplanes which lie below the frontier. Okay. So consider only those hyperplanes which lie below. Question is, if you consider all the hyperplanes lie below, some gap will come up. You see the red gap? When will this gap become zero? You got the analogy? The primal is trying to push down the y-intercept. The dual is trying to increase the y-intercept. The constraint is that the hyperplanes for the dual should lie always below the frontier of the primal. When do you think that gap will become zero? Yeah, when the 2 points intersect. But when will that become? So you're just translating my point of zero duality gap to the fact that they should intersect. They should be the hyperplane should touch. That's what you're saying, right? The hyperplane should be able to touch. So when will it touch the frontier? When it becomes a supporting hyperplane. So you see what we did in one of the first few lectures, the supporting hyperplanes being so critical, whether it's defining gradients. Right? So when this becomes a supporting hyperplane, and when is supporting hyperplane guaranteed to exist? If it's convex, it's guaranteed to exist. So if this I region were convex, then, well, convex with some conditions, it should contain the boundary, etc., closed. Because it's possible that I is also open. Then we'll have a problem. If I is open, there'll be a problem. So it's not, just blanket convexity is not sufficient. It's a little bit more you have to do. There's something called Slater's conditions and all that. But you understand, convexity plus, little bit of convexity plus something more. If I looks like this, right? Here you're trying to push. So if it looks like this, and this is I, then we seem to be fine. Okay. So what I'll do is, I'll also present a slightly annotated version of the same plot. Okay, here. So what you see, these curves are the D stars, the intercepts of the of the L star are the D stars. So we'll give it a name. The solution to the primal will be called P star, right? Primal solution is P star, and dual solution is D star. So P star is greater than or equal to D star. This is P star, this is D star. So primal optimal original optimization is pushing down the intercept of this region. Dual problem is pushing up the y-intercept. That becomes possible that they'll coincide when there is convexity, apparently. So this is the dual problem. Now, the duality gap will vanish when there's convexity seems to be our kind of conclusion from this analysis, right? So this gives us this. We'll go back to now the KKT conditions, what I wrote on the left side of the board. When there is zero duality gap, right, then the KKT conditions are implied. Right? If primal and dual are the same. I'm not going through the proof. Right? So the claim is these are necessary conditions. The KKT conditions are necessary conditions for not only optimization, but also for zero duality gap. So not only are we saying this will give FFX minimized, but this will also create zero duality gap. Is this clear? And you can kind of write this down. See, I mean, if you write the gradient of the Lagrange function, set it to 0, and put all these conditions, you're basically operating in primal and dual feasibility. you're optimizing with respect to lambdas and mu's both, right? So if you're able to satisfy all of this, you have the zero duality gap implies KKT conditions. The question is, do well KKT conditions give you zero duality gap? So again, I'm repeating. This is only saying that if there is zero duality gap, then KKT conditions are necessary. If there's an optimal point X star and feasible, primal feasible, zero duality gap, sorry, KKT conditions are necessary. If you have a dual feasible lambda mu maximizing L star, then KKT conditions are necessary. But nowhere we have said so far that KKT conditions are sufficient. For sufficiency, what will you need? You need this condition, that the two are able to actually meet, right? That is convexity. Okay, so I'm again emphasizing convexity is not part of necessary conditions. I've just written the whole thing again, for your understanding. I mean, if X hat is the argument of all of this, then there must exist lambda hat and mu hat and following conditions, which are the gradient of the Lagrange should go to 0 with respect to lambdas. Sorry, X's complementary slackness should exist. So basically, primal and dual feasibility. That's all I'm saying. Hyperplane has to exist for? No, hyperplane is corresponding to the Lagrange function. Because in the case of Lagrange is what you're looking at, pointwise maximum of L's, right? As a function of lambda I and mu. So lambda and mu, it's linear. That's why it's hyperplane. Not any X. So if you had KKT conditions and convexity, then you have zero duality gap. So this is the sufficiency, right? If the function f is convex, gi's are convex, and hj's are affine, right? When I say hj is also convex, minus of hj is also convex, what does that mean? If I'm going to use hj greater than or equal to 0 and hj minus hj greater than or equal to 0, basically affine, right? So if HJs are affine, GIs are convex, F is convex, then the KKT conditions are not only necessary, but they're also sufficient. Is this clear? Right? So what are we saying? The sufficiency is only because of convexity. I mean, owing to convexity. And all the algebraic expressions of projection that we showed in the earlier table for projection can be derived using these KKT conditions. So by the way, that tables that I showed you earlier, actually, there's this nice book by Amir Beck. I have pointed to that. Oh, what is this? Yeah, I pointed you to that. There's a book called First Order Methods in Optimization. You'll find some chapters available online. And I've just taken the projection operations from there. The table I've attributed it to this book. But you can derive all of those, as I said. Remember the tables. All of them can be derived using this set of conditions. I talked about the calculus, right? Calculus of multiple constraints. Exactly, that's what is manifested here. Okay. This table, some of the entries I've reproduced. So if you look at my extra optional material from previous offering, right, I go through very detailed geometric interpretation of necessary conditions of optimality, which I did for only one constraint. I show that for multiple constraints. Same intuition. Geometric interpretation of zero duality gap and connection with convexity. I go through a lot more details. In fact, not only that, I do proofs as well. Right? I go through the Slater's constraint qualification, weak and strong duality theorems and their proofs. I go through, see, now this just, once you get hang of this entire primal dual understanding, there's so many things you can do. For example, You can look at the Frank-Wolf method. You can look at dual ascent. We looked at one notion of dual, but there are other duals as well. Right? Have you heard of any other dual? It's called the Lagrange dual. Sorry? Huh? Fenchel dual? Right? So there are Fenchel duals. So there are other duals as well. So as I told you earlier, the whole notion of dual is, I mean, one is to carve out a sculpture from a stone. The other is to fill into a cast and create a murti, right? So the dual, there are multiple dual views. And so I have pointed to those, some of those old YouTube lectures. But I guess you got an important glimpse into or handle into how to deal with duals. Now, what I do is in this material, I'm self-reading material. You can actually see, and this is mandatory. Okay, it's mandatory for you because it's a support vector machine-based formulation. I'm assuming you would read it up. You will understand from a basic course of machine learning. What we have there is minimizing 1/2 norm W square plus C times some Xi plus Xi star. I won't get into what these are. Xi and Xi star are the slackness variables. W norm W square is basically is to do with the margin. Right? You're trying to maximize margin, and that reflects as minimizing 1/2 norm W square. Of course, there's a regularization interpretation also of this. Right? And then you have all these constraints, just saying that, okay, I want separation of points, but sufficient separation through a supporting hyperplane. Now, so that's a sufficient slackness. So this epsilon is basically the sufficient margin separation. Okay, so now if you consider the Lagrange multipliers, so let's say alpha is a Lagrange multiplier for the first set of constraints, inequalities, so multiple inequalities, okay? For each point I, you have one inequality. If you consider alpha star for the second inequality, mu I for the xi I greater than equal to 0, and mu I star for the xi I star greater than equal to 0, you have 4 sets of Lagrange multipliers, lots of them. You write down the Lagrange function. Quite complex, means a lot of terms, nothing to be scared of, right? You have this 1/2 norm W square plus C times this, plus, as I said, alpha times the first inequality, alpha star times the second set of inequalities, mu I times xi I, and mu I star times xi I star. So now you try and define the Lagrange dual. I mean, this is a Lagrange function. Now, how do you get to the Lagrange dual? So here what we say is, okay, if here we kind of invoke convexity. So what did we say? If there's convexity, then under they basically get zero duality gap, right? So assuming, I mean, you work out the convexity properties, which these are all convex, right? These are all convex. Nothing to sweat about, right? So if you differentiate the Lagrange with respect to W, you'll get this, right? So using the KKT conditions as sufficient and necessary conditions. That's what we are taking liberty now. We have applied the first KKT condition, right? Which was the first condition? The gradient of the Lagrange function should go to 0 with respect to the primal, which is W. But not just W. I have to differentiate with respect to the Xi's as well, because Xi's are also part of the primal, right? The Xi slackness variables are part of the primal. So there, if you differentiate, very interesting. The first set gives you W is a linear combination of the phi xi's. The second one says that alpha I and mu I should sum to C. The third says with respect to Xi star, alpha star and mu star should also sum to C. Right? And if you differentiate with respect to B, there's also B offset. Then all the Xi's and Xi stars together should cancel out each other cumulatively. And then complementary slackness, very interesting. That mu I Xi should be 0, mu I Xi star should be 0, and then alpha times or alpha star times those respective hyperplanes should be 0. Hyperplane equations. Now, what happens is interesting, right? I just want to draw your how this duality brings a very different degree of charm to this entire analysis. So, alpha I turns out to be between 0 and C. If alpha I turns out to be between 0 and C, do you know what happens? Just based on the complementary slackness conditions. I go back to the previous, right? If alpha is between 0 and C, if alpha star is between 0 and C, okay? So you had complementary slackness conditions here. Right? If alpha I star is between 0 and C and alpha, so if moment alpha I is between 0 and C, then mu I is also between 0 and C and mu I star are between 0 and C. Moment mu I star and mu I are between 0 and C, then xi I should be, xi and xi star should be exactly 0. Right? If mu I and mu I star are non-zero, then xi has to be 0. If xi is 0, then what happens? So look at all of these, the cascading effect. Right? By the way, if alpha I star is between 0 and C and alpha I is between 0 and C, then these inequalities are also equalities. Right? These are 0. So this will go to 0. This will go to 0. Xi I will go to 0. Xi star will go to 0. What will happen for those points with alpha I and alpha star between 0 and C? Yi minus W transpose phi xi minus B equals epsilon. B plus W transpose phi xi minus Yi equals epsilon. And these will turn out to be what we call the support vectors, right? So just by applying, right? So the visualization is you have the separating hyperplane, so and we are supporting hyperplanes. So for all points x, if alpha I is between 0 and C, or alpha I star is between 0 and C, then what happens? You'll have Yi equals W transpose phi xi plus B minus epsilon. And on this side, Yi, this is minus 1, is W transpose phi xi plus B plus epsilon. So these are the supporting hyperplanes, minus epsilon and plus epsilon, right? These are supporting hyperplanes. So alpha i's, which are between 0 and C, give you exactly the support vectors. Alpha i's can be equal to 0 also. I'm saying those points will not be on the support vector. Those can be anywhere else. All we are trying to say is if alpha is between 0 and C, then those will correspond to these points on the supporting hyperplanes. That's all. That's the interpretation. Other alphas can be anywhere. But this gives you a sparse solution. I mean, sparse set of support vectors which can be used to compose, right? So conclusion is that, right? All of this, right? I mean, you can conclude alpha between 0 and C gives you exactly the support vectors. The support vector regression. So for support vector regression, since the original objective and the constraints are convex, any W blah 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 that satisfy the KKT conditions give optimal solution and also sufficient, right? So now we take this a little forward, right? Now all this is fine. Now what happens if we substitute? W was a linear combination, right? If I substitute for all, W as a linear combination of the alpha I, W was alpha I times phi xi, right? Okay, so that was the other important point. W itself is alpha I times W phi xi. I mean, it involved both. Yeah, W was of that forms. So now when you write on the dual objective, so you have this weak duality theorem, you substitute based on the KKT conditions. We are working backwards from KKT conditions. So substitute for this W star, right? What will you have? Norm W star, so norm W square will give you a dot product of the phi with phi's. Phi xi transpose phi xj. Right? When you substitute them, I mean, just a little too verbose, but yeah, you'll get this little complex thing. So you'll have phi transpose xi, phi xj into alpha I minus alpha I star, alpha j minus alpha j star, and so on. So what is interesting is you can now actually start operating only in terms of dot products. Everything is in dot products. B will be in terms of dot products. The solutions are in terms of dot products. So even if your original files were in a very high dimensional space, you are able to now compute it's using the dual, the solution in the space of the dot products of pairs of points. Right? So that gives you the kernel function. Phi transpose phi xi dot product with phi xj. So what is W? W is, right? So you will find that W is in this dot product form, F is in this dot product form. So this is the kernelized expression. So this is what you get, right? So you have a dual problem, which is just in terms of dot products, just in terms of dot products. So now you can invoke a nonlinear kernel, solve the problem. In fact, even if the phi's are infinite dimensional, in the case of polynomial kernel, your dual solution is very much more efficient. You don't have to get into an infinite dimensional W. So if I mean I've given an example, if kx1 x2 is 1 plus x1 transpose x2 whole square. So you can find out what is the phi that will give this complex. It's going to be at least 5 dimensional. I think it will be 5 dimensional phi, right? Oh, it's just a 6 dimensional phi. Sorry, there's a 1 as well. So phi xi basically lies in a 5 dimensional space. There's a 1 at the top just because of B, yeah, bias. But to compute K, we don't have to really enumerate the 5 dimensional phi. We just need to compute 1 plus x1 transpose x2 the whole square. Right. So this you can solve this dual problem efficiently. Now, this is an example, right? Why duality yields itself to more efficient solutions, sometimes more interpretable solutions. And as I said, sometimes the primal is not even convex, but the dual, you're dealing with a concave maximization. But there is a gap. There's no free lunch. Either you get convexity and no gap, or without convexity, you get a gap, but at least you're able to solve a concave optimization problem. So, yeah, so this is the whole idea of kernels, is support vector regression. Right? So you can do the same thing in ridge regression, which is without support vectors, support vector machines also. Even with ridge regression, you can come up with a kernel formulation. Okay, so this kind of, I hope you got a good feel, right, of optimization and machine learning through the use of Lagrange duals, weak duality. What I'm going to do is I'm just going to get you started with the next topic. Just give me 5-10 minutes because we have really spent a lot of time on the seminar presentation. So just give me a few more minutes today. I want to just get you a glimpse of some of the algorithms, principles behind discrete optimization. Right. So we've done a lot of continuous optimization, right, and constraint optimization. We got concave maximization from non-convex constraint problems as well, like we did today. Discrete optimization, I give you a lot of problem motivations. I think there's sufficient motivation there. But how do you really solve them? And you'll find that the flavors are similar. The approaches can be different. But only thing is, it's not as coherent as continuous optimization. It's quite disparate. So let's look at some ML. I mean, I think this was our favorite problem where you're trying to have a scoring function over elements in a ground set V, and you want to score such that a subset is as representative as possible, as diverse as possible, right? So there's some nice slides that I borrowed from Jeff Bimes, etc. There's some good books that refer to this class of optimization problems. Yeah, we also have some more of our own Ichkai tutorials, so you're welcome to go through those tutorials in detail. So you recall these were the different objective functions where we dealt with discrete optimization, right? Map inference and probabilistic models, feature subset selection, data partitioning, and so on. These are examples from our earlier lectures. So I'll deal with this very quickly with this class of functions called submodular functions. The idea behind submodularity is that while general set optimization, combinatorial optimization is very hard, if there's a structure to the space of functions, then maximization as well as minimization. I won't talk about minimization, but both maximization and minimization are able to exploit that structure to different degrees. So what is submodular functions? Basically, functions that have diminishing returns. So like concave functions, right? We saw pointwise minimum of multiple convex linear functions was a concave function that gave us the Lagrange dual. This is always concave. What is concave? Diminishing returns, right? Concave functions always have this curve. Well, submodular functions are similar in that sense. You're saying f of a union v minus f of a is greater than or equal to f of b union v minus f of b. The addition you get by adding a v to a, which is a subset of b, is more than the value you get by adding v to a superset, which is the b. So as you keep growing the set, there is diminishing returns, right? There's diminishing returns in this room as you keep on switching more bulbs. The first bulb makes the biggest difference. So diminishing returns is pretty ubiquitous. You're basically, whether it's bulbs in this room or sensors in this room, every additional sensor is just going to add less incremental value. It doesn't mean that it is decreasing. Diminishing doesn't mean decreasing, okay? Please be very careful. Right, so here's an example of this same balls and urns. So in this left-hand side, A, you had exactly 2 distinct colored balls. So when you add a V, which is this, you get 3 distinct colored balls. Whereas on the right-hand side, because it already has 3 distinct colors, you add the blue one, it is still just going to give the same 3 distinct colors. So 3 minus 2 is greater than or equal to 3 minus 3. So the negative of submodular function is a supermodular function. Just like the negative of a convex function is a negative of a concave function is a convex function. So good question. This is for all V. For any subset A of B, for every subset A of every B, and for any V, this should hold. This inequality should hold. Okay, so the reason I was in a hurry is, so you saw the connection today between convexity and concavity through Lagrange dual, right? It's interesting, they resurface. Question I have is, do you think, okay, the homework problem, do you think submodular functions, if they are like concave functions, then supermodular functions are going to be exactly like convex functions? Do you think that submodular functions may have only properties like concave functions, or do you think they'll have properties like convex functions as well? Okay. And my hint is, the analogy is not straightforward. Okay. It's not that submodulars functions are diminishing returns like concave functions, supermodulars functions therefore are like convex functions. What is easy to maximize, convex functions or concave functions? Concave functions, right? That's why we got excited when our Lagrange dual was a concave function to be maximized. He said, wow, good. A dual problem is a concave maximization problem. So do you think that maximizing submodular functions is going to be an easy task and minimizing supermodular functions is going to be a hard task? What are your thoughts? So I'm going to leave you with some questions for today, and then I'll just conclude in a few more minutes, right? So submodular functions, you can, all these examples of diminishing returns, the more items you buy, the more the discount happens, right? And all these big supermarkets leverage this principle. Or, if you're looking at labeling or summarization, again, more extensive the summary you produce, the less additional value you're adding. Or sensor placement is the example I gave in the class. Trying to place sensors, there's going to be diminishing returns. Modular functions, on the other hand, are exactly like linear functions. Since I'm trying to break the tension between concave, convex, and submodular, supermodular, Modular functions are like linear functions, are like what we saw, right? Hj's are linear. So we were happy taking Hj less than equal to 0 and minus Hj less than equal to 0 because both are convex as well as concave. So modular functions are basically those which decompose into element wise application. So f of s is summation over the weights of the elements in E for each element E in S in the case of modular functions. So you can basically do the following: f of A union E minus f of A is W of E. So the inequality in the case of submodular function becomes equality in the case of modular function. So modular functions are therefore both submodular and supermodular. The negatives are also submodular, right? So there's another notion which, so submodularity and supermodularity by themselves are not sufficient in practice to even look at optimization, efficiency and so on. What you often need is also another property called monotonicity. And this makes sense for discrete objects, right? So monotone means f of A is less than equal to f of B, right? In this case, while I said that the illumination in this room is a submodular function of the bulbs, it's also interesting that the illumination is a monotone function. The more the bulbs are light up, the illumination is going to increase, right? Only in such cases, algorithms become more interesting. If monotonicity, I mean, algorithms can be interesting when otherwise, but guarantees become feasible. Good algorithms, algorithm convergence, good approximation bounds, for example. So this monotonicity goes implicit with many submodular functions we state, but you have to understand it's a different property. It's influence in social networks. One of the most beautiful examples, and this is going to be my last important example, is entropy. In fact, a lot of submodularity was always discussed by Shannon. If you look at Shannon's properties of entropy functions, you'll find that, well, actually, they are properties of submodular functions. So entropy was the oldest, very well-known submodular function. Entropy happens to be not only submodular, but also monotone. Right? Entropy keeps increasing as you add variables. Right? You can show this. Entropy of A and this C together is greater than or equal to the entropy of A alone. Now, information gain is an example of derivative from entropy, right? F of A is entropy of Y minus entropy of H of Y given XA. Right? So, so it's not necessary that submodular function has monotone. Okay? Monotonicity and submodularity are different properties. And not every monotone function is submodular. Obvious. Right? Here's an example where you keep adding elements. It's monotone, but it's not submodular. You can verify for yourself. Right? AB is a superset of B and A. But it's not that by adding B to or empty set, right? Empty set is 0, B is 1. But when I add A to B, the gain is 2. When I add A to the empty set, the gain is only 1. Okay, so this is certainly a counter. So one interesting thing about these discrete functions is a lot of counter examples you can give. So if in your end sem you get a question, one of the best ways to try and find is a counter example. Okay, not difficult at all with discrete functions because most properties don't hold. Most properties don't hold. Right? So I already gave you a hint about the question I've asked earlier. Are submodular functions like concave functions? Maximizing is it? My answer is it's not easy. Right? So and the answer lies in a lot of negative examples, contradictions. Right? So we have as I said, submodular and supermodular functions. Modular functions are exactly in between. I want to just end with some properties. So there are interesting properties like convex combinations of submodular functions remain submodular. When we did convexity, one of the first things was calculus, right? What preserves convexity? right? So you can think of if there are examples that surface in your own paper studies or projects. So if you take a linear combination of submodular functions where lambda i's are all, you don't have to be convex. Lambda i's are just positive. They should not be, they need not be convex, but they should not be negative. So submodularity is closed under non-negative linear combinations, right? So for example, if you take a probabilistic combination of multiple submodular functions, it's going to remain submodular. Okay, so that holds, right? And it's very easy to show. A very basic proof is just show by the original diminishing returns property. More properties. So if you consider intersection, so let's say if I define f dash to be the original function f defined on intersection of the argument with some fixed set. W is a fixed set here. I think of W is like given here in blue, red, W is fixed. So if I say intersection S fixed with a fixed intersection W, then this function is also submodular. This is called restriction. I'm restricting S to W. The second is conditioning. Every time I ask F on S, I also include W, S union W. So that is conditioning. So if I condition, it's still submodular. If I restrict, it's still submodular. And the third is reflection. I ask you to evaluate on S, and what you do instead is evaluate on the complement of S, right? That function is also submodular. So I give you F, you always evaluate on the complement, submodular, that is reflection. I give you F, S, and you always evaluate on its union with a given W, fixed W, that is called conditioning, that's also submodular. I give you S, you always take its intersection with the fixed W and then evaluate its function. Original function submodular implies even the restriction is submodular. Right, so all these are for fixed S, for fixed W, sorry, fixed W. So I'm going to end with this slide, kind of homework. Now I gave you one definition of submodularity, but a very practical, useful definition is another definition of submodularity, which is called the union intersection property. Okay. So what's a union intersection property? So remember that f of A union S minus f of A is greater than or equal to f of B union S minus f of B. A subset of B for all S. That is the first definition. But there's another definition, which is f of A plus f of B is should be greater than or equal to the f of A union B plus f of A intersection B, right? Now let's take the example of modular functions. What happens for modular functions? What happens in this inequality? It becomes equality. Likewise, for union intersection, what happens if you take modularity? Modular functions, inequality will become equal. The size of A plus the size. So classic example of modular function is cardinality. The size of A plus the size of B is the size of A intersection B, which is all the common elements between A and B. And because this intersection is counted twice in A and B, so I can count intersection here and I can count intersection in A union B along with those elements in A which are not in intersection, along with those elements in B which are not in intersection. How do you prove the equivalence of the two? Okay, and I'm going to end with this, give you a hint, right? How do you prove the equivalence of the two? Very nice. I mean, this is one of the most elegant proofs, and many other proofs in this space can be done on similarly inspired principles. What did I tell you? I described in terms of elements in A, elements in B, elements in A not in B, elements in B not in A, right? So imagine so I'm just going to give these names. So, and this is how you can prove it. So I'm going to say these are elements in A which are not in B. That's X. elements in B, not in A, I call them Y. And if you want, you can call, I mean, there's A intersection B, right? So to prove this, what you could do, so you can view this A union B as what? What is A union B? In terms of X, Y, X union Y union A intersection B, right? The common part. So the proof you can try and prove it by taking A intersection B, adding one element at a time from X, adding one element at a time from Y, and use the diminishing return property. Okay? You understand? And this is basically modularity inspiration, right? You're saying, well, if they were modular, I would have had equality if I take element wise, but now that's not going to be the case. It's right. So step is you define this. Okay, I have slightly defined differently here. So let me, okay, in the slides I have defined it differently. So I have defined this X as A intersection B. Okay, sorry. X, this is Y. This is Z. X is A intersection B. Okay, sorry. Okay, so what have I done? I have written A and B in terms of X and Y. A is X union Y, B is X union Z, and A union B is X union Y union Z. Then the steps are very simple. You just need to compose your A's and B's in terms of X and Y's. But when you write it down, you have to write slightly differently. Instead of writing, this is the key. This is the key step. F of A is written as the largest set, right? Which is the largest set? X union Y. Minus one element subtracted from X union Y. Right? And then from that new element, again subtract. So it's basically, what is it? F of A, which is F of X union Y, is F of X union Y minus F of X union Y minus one of those elements Y1 plus F of X union Y minus Y1 minus F of X union Y minus Y1, Y2, blah, blah, blah. So you kind of write it, same, you remember the same telescopic summing, same principle of telescopic summing. This term will come twice, every term will come twice except the first term, which is X union Y, which is the original set. Then you need to apply diminishing returns at every step. You got it? That's a basic idea. I'm not going to complete it here. It's a homework problem. So I think if I get some time in the next class, I'll try and give one or two more hints. But the key is if you get hold of such telescopic summing based proof methodologies, right? Most of the discrete optimization, at least the very frequently encountered discrete optimization problems, are built around such proofs. We'll end. Let's see if we get time in the next class. I'll take it forward. Otherwise, I think there are one or two presentations pending, which couldn't be completed. So we'll hopefully get at least half an hour next time. Thank you.